Yeah, this ties me to my Mac laptop. My desktop is Windows. So, I mean, they don't have a Windows version as far as I.
Even if they had a Windows version, you wouldn't be able to reclaim your purchase and such things. That doesn't happen between Windows and Mac, I think.
Yeah, yeah, yeah. I would have to purchase it separately, I guess.
Yeah.
Yeah. Anyway, doesn't matter. Okay. So, yeah. So the last part was we were trying to show the following. So, okay. There exists, in fact, two outcomes. Two outcome measurement. M such that so the Schatten L1 now between rho and sigma is equal to the the vector L1 now. You should have turned the eraser mode on. Clear one automatically. So here was the true. Okay, so when I said two outcome orthogonal measurement, as you'll see, there are two classical outcomes. Okay, so for example, M rho will be a probability vector with just two coordinates. And so let me write down what it will be. So this will be trace of M plus rho, and the other is 1 minus this, which is also trace of M minus rho. Okay. So when I say so when I say orthogonal measurements, then I mean that M plus M minus are orthogonal. Orthogonal, something wrong with the responsibility. Okay, are orthogonal projections and adding up to identity because of Liouville elements. Okay, so orthogonal projections means the following. It's a Hermitian operator. So first of all, these are Hermitian. I think it's a nib. Hermitian operators, and yeah, and projection means the square is itself. M minus square is M minus, and it's a measurement. So this condition we know. So for our traditional definition, so this is the identity operator. Okay. So orthogonal projections means that the two outcomes, you can see there's M plus and M minus. So the outcomes are labeled by the classical symbols plus and minus. And they are Hermitian operators. Okay. And their square is itself. So this is the idempotent property. So Their Hermitian operators means that in the appropriate eigenbasis, their eigenvalues are real, and their square is itself, which means that the eigenvalues can be either 0 or 1. So now you look at the eigenspace corresponding to eigenvalue 1. So that's the subspace, and this geometrical is just a projection onto the subspace of ones. Okay. So M plus is one such thing, M minus is another orthogonal projectors, and when I say they add up to identity, it means that their respective supports are orthogonal complements of each other. So the support vector spaces of M plus and M minus are orthogonal vector spaces, and together they span the entire space. So this is what it means. So basically, so this is projection onto projection eigen space. Okay. Is this clear? Okay.
One question, just to
Yeah,
clarify.
yeah.
The M row is the they are the probabilities of measuring plus and
Yeah,
minus.
yeah.
The trace of
So
them, the trace
Trace
of
of
the
trace of this. This is the expression, right? So
Yeah.
it's a two outcome measurement. I get the plus outcome with this problem. So this is the same as the measurement operator. So the measurement operator was what? They were positive semi-definite matrices. So of course Hermitian positive semi-definite, and they add up to identity. When I say orthogonal
Yes.
projection, there is this additional property.
So is this orthogonality, like where is this property coming
yeah.
from?
So I mean, one thing which
Yeah.
you
So
can get from
let me answer this. Let me show geometrically what is this. Okay. So let me remind you of something which you may have studied in linear algebra. So orthogonal projection is this geometric thing. So here is a vector V, okay, and this is let us say my M plus. Okay, this is basically the support of M plus, the one eigenspace M plus, and the geometric operation is you drop a perpendicular to this subspace, okay, and what you get here is MV. Okay, this is a perpendicular to the subspace. So that's where the word orthogonal comes from. So, whereas in linear algebra, a projection operator is any matrix which satisfies like
square
m
of
square equal to m.
the idempotent
Yeah,
property.
yeah,
Yes. Okay. Yeah, I recall.
yeah. So the
Yes.
additional thing of the orthogonality comes from Hermitian. Okay. So the
Okay.
difference will be is that like if I'm doing all my linear algebra with a non-orthogonal basis, then I mean like I have something like this, then this would be the projection. Okay. Let us say this is NV. Okay, so this is non-orthogonal projection on onto okay. So the you can see, I mean, why the square has to be itself, because whether you're in the left or orthogonal picture, in the non-orthogonal picture, you take a vector, you project it once, and if I project it second time, I will get the same thing. Okay, so that is always there. Like I mean, you're projected once, then you're done. I mean, it remains the same after that. Okay, but the difference is here when you go from V to MV, that line segment joining them is orthogonal to the subspace. Here there is no such property. So of course, orthogonal projections make sense if there's an inner product over the underlying vector space. Or else, what do I mean by orthogonal? Okay, and again, Hermitian operators make sense only if I can define the adjoint, right? Like M plus is Hermitian means M plus equal to M dagger. But adjoints I can only define if there's an underlying inner product. Okay, so just plain projections you can define for any vector space, basic linear algebra. But if you're talking orthogonal projections, you can only define it for inner product space. So I suppose this should be familiar to you. I'm just
Yes.
jogging you. Okay. Yeah, Shantan, you are saying something. Huh? Shantan, were you saying something?
Yeah. So I was just saying that maybe this might, yeah, I mean, of course, what you said is the thing, but here is a more direct explanation. So if you
Okay.
take m plus product m minus, it's the zero operator. And that you can see from the m plus plus m minus equal to I. So basically what you do is, so these are positive operators, right? So if you take the product of m plus and m minus, what you see is that you just take the trace. The trace will be zero. That is easy to work out. But since m plus and m minus are positive, and because they are projectors, you can, it's a slightly, it's requires a slight bit of thought, but that would imply that the eigenvalues of m plus and that m plus times m minus is eigen decomposable. But not only that, it will also imply that the eigenvalues are zero. So
Yeah.
that is
So
essentially what it.
basically, you are saying even this operator, yeah, after some thought. Okay. So
Yeah, I mean, it's a
yeah,
it's a fair bit of thought. It's a fair bit of thought,
a fair bit of
and
thought. Yeah.
yeah, but
So exercise.
exercise, yes, and you have to use the fact that they are projectors. I mean, this is not true for any arbitrary positive operators. This is only true for projectors.
Yeah. Yeah. So actually, Shantan, a good point. So this thing that m plus uh, this m plus times m minus equal to 0, this will hold if you have a complete system of projectors in general. They don't have to be orthogonal projectors.
Oh,
Okay. Yeah. So really
oh,
the
right,
orthogonality
yeah.
has the Hermitian property. So
Okay.
basically, I mean, what is a complete system projectors? Let us say I take a complete system of two spaces. Okay. So in the non-orthogonal picture, this is one space and I have another space. Fine, it is not orthogonal to it, but I have chosen my basis to be compatible with those two spaces. So I have chosen my basis for the entire space. The first set of basis vectors come from subspace 1. The second set comes from subspace 2. And together it's a linear independent set. Okay. So with respect to this
Okay.
decomposition,
I see.
yeah, with respect to decomposition, I can define n plus and n minus. And all I'm saying is that the n plus and n minus are linearly independent. That is what this operation is saying. So
Right.
this is true from anything. I mean, this to prove that the product of n plus and n minus is 0, I only need the adaptive identity and the idempotent property. The orthogonality is
Okay.
really the Hermitian.
Oh, I see. No, I got
Okay.
that. Okay.
Yeah. So
Very
again,
cool.
I mean, this is something you have probably done in your linear algebra course, but yeah, you should refresh your memory. Yeah.
So I mean, one thing is that this trace thing, trace zero, that's
Uh-huh.
like, I mean, this is what I sort of look at it like for after like talking to Pranav a lot. So this is the inner product. The trace is between inner product between between operators, right? And you can think of it as over some quantity which defines the overlap between spaces. So this trace being zero essentially means that the spaces are orthogonal.
Correct.
Yeah, I mean,
Yeah.
so
So yeah.
that's the
So
geometry.
yeah. So I mean, of course, when you're talking inner product between operators, like the underlying vector space, inner product space, because
Yes.
last time I think I told you, like to define the inner product, I actually have to put a dagger on the first matrix. Okay. But because it's Hermitian, like m dagger is equal, m plus dagger is equal to m plus. Okay. So yeah. So of course, yeah. So you can indeed treat this as the inner product between the operators m plus and m minus. Okay. And when we were discussing the partial trace, we have talked about this. So I mean, you can very validly,
Huh.
think of trace m plus m minus as an inner product. So just telling you that is m plus. That's the and indeed this is equal to trace of m plus dagger. Fortunately, dagger let me try this again. So this is defined to be the inner product between m plus and m minus. Yeah, so this is again some notations which we did last time. Okay. Yeah. So more comments, questions. So is the geometry clear? Okay. So let's proceed. Yeah. So I claim that I can in fact come up with a two outcome orthogonal measurement satisfy this, and two outcome basically means m rho will look like this, and m sigma, of course, the same thing. Trace of let me write it down somewhere. So m sigma equal to trace of m plus sigma trace of m minus sigma. Yeah. So I just define what is m plus and m minus, and last time it was fast, so I'll do it again. So I look at this matrix rho minus sigma. So this is Hermitian, right? Difference of two Hermitian matrices. I have to recalibrate this pen. There's a button on the pen which got pressed, and I don't know how that happened. It pasted the Zoom link for this. Okay, so this is Hermitian, and it has trace 0 because those were trace 1. Oops, trace 0. Okay, so because it's Hermitian, the rho minus sigma will have real eigenvalues. Okay, so some are positive, some are negative, some are 0. Let us say I club the 0 in one of them, maybe in the positive. Okay, so and trace 0 means the sum of the positive eigenvalues is equal to the sum of the negative eigenvalues. So I can now write this as equal to, so the notation is, so it's which notation? Subscript plus minus rho minus sigma, subscript minus. So this is like this matrix rho minus sigma restricted. So write in the eigenbasis and restricted to positive eigenspace. And this is restricted to oops. Okay. Okay. Yeah. So this is okay. So I hope this is clear. So the matrix rho minus sigma, I can write it like this. Restricted to positive eigenspace, restricted to negative eigenspace. Yeah, and there's a minus sign here. So essentially, rho minus sigma is also a positive semi-definite matrix. Okay, I restrict to the negative eigenspace, but then I take the negation of those negative eigenvalues, and of course the remaining space it's all zeros. So what do I get? Both these are positive semi-definite matrices. The difference is the Hermitian matrix rho minus sigma. Then rho minus sigma is trace 0. So In fact, the trace of rho minus sigma plus is the same as the trace of rho minus sigma minus. Okay, and they have orthogonal support simply because this came from the eigenspace decomposition. Okay, so is this clear, Hari?
Yeah.
Yeah. Okay, so that's it. So now I can define my favorite m plus. So m plus is defined to be span or whatever support. That's what I mean by span.
Projector onto the span, I think. Right? That's the
Yeah.
something
So
like yeah, something
I'll
like
just say support. Yeah. I mean, we know what it means. Yeah. So support of Hermitian matrix is basically the non-zero eigenspace. So support of rho minus sigma plus. Okay. And put in the zero eigenvalue also with n plus just for the record. And it's the support of rho minus sigma minus. And now you can see that m plus and m minus are orthogonal spaces, and together they span the entire space. Okay, so this pair is an orthogonal projection, orthogonal measurement. Okay, all the properties of an orthogonal measurement. Okay? So now I can write down. So what is m rho? So trace of m plus rho. Trace of m minus. I think this is a fancy. Trace of m minus rho. Okay. So now if I look at the L1 distance between the probability vectors m rho and m sigma, so what is this? It is trace m plus rho minus trace m plus sigma absolute value, and then plus yes m minus rho trace sigma. Okay. So now this is trace m plus.
so this is just the one now between two distributions, right?
Yeah, just a one norm into distribution. These are two outcome distributions, so I've written it out fully. Put the absolute value sign here. Yes. Okay. But as you can see from the definition of m plus, this is nothing but okay. There's a trace here, trace of rho minus sigma plus, and this is trace of rho minus sigma minus. Okay. So remember, rho minus sigma subscript minus was a positive semi-definite matrix. That's it. And this one is okay. Yeah. So what have I done? Like I've taken the matrix rho minus sigma. The positive eigenvalues remain the same, and the negative eigenvalues I've just converted to positive. So in other words, I've taken the absolute values of all the eigenvalues. Okay? Or in other words, these are the singular values. So this thing is the sum of the singular values of rho minus sigma. So there's even notation for that. So take any Hermitian matrix, take the absolute values of the eigenvalues. So the resulting matrix is suggestively denoted as absolute value of this. So by definition, this is this. And this, you can easily see sum of singular values is the shattered L1. Okay, so we are done. So here is a two outcome measurement, which we have finally done. So here is a two outcome measurement, which achieves the one norm, the shattered one norm, shattered one distance between rho and sigma. Okay. And in general, any measurement, non-orthogonal, orthogonal, any measurement gives rise to probability distributions, and the L1 distance between the probability distributions, we have argued, is less than or equal to the trace distance between the distributions. So here is like the first idea that you see, that the trace distance seems a good figure of merit to talk about distinguishability of two quantum states. So if two quantum states are close in the trace distance, that means no measurement can distinguish between them. Right? So measurements. So one way of learning about a quantum state is you do some measurement in the lab. Okay, and suppose you don't know whether the quantum state will be rho or sigma. You know it's one of them, and you want to do a measurement and find out. So the measurement will give a probability vector, and you want to know whether the probability vector is m rho or m sigma. So the so the error that you will get will depend upon how close they are. Okay, and for probability vectors, we know the L1 distance is a good figure of merit for closeness, and that is one of the reasons is that I have a probability vector, and if I take a subset of the coordinates and then look at what is the probability mass given to the subset by the first probability distribution minus the probability mass given to that same subset by the second probability distribution, this will again be upper bounded by the one. Okay. So the one norm between probability distributions is a good figure of merit to talk about the closeness or the distinguishability between probability distributions, and that is further upper bounded by this. Okay. And now, when you take the general picture, so the classical picture of taking a subset of the coordinates and looking at the probability, what you call the events. This is just a special kind of like distinguishing algorithm that I can do to try and distinguish between two probability distributions. A more sophisticated one would have been a private coin algorithm. And we argued in the classical half of the course that the difference in probabilities that a private coin algorithm would give between two probability distributions is again upper bounded by their one norm. Okay. In fact, one norm divided by two. We have checked that. So now, even private coin algorithms are special classes of quantum measurement. So, I mean, if you are embedding like classical probability distributions as diagonal density matrices. So what this says is that you do any measurement on a quantum system. Okay. And well, now I'm talking of basically, I mean, one measurement outcome. The difference between the two, between the outcomes is upper bounded by half of this one norm. And then there are measurements which can even achieve that. Okay, so this actually is a generalization of something that you already have seen in classical form, but I mean, it may not be immediately obvious. But the essentially, like, it's because of this lemma, we can actually think of the shattered one norm to be the true generalization of the L1 distance between probability distributions. Okay? And it is strongly tied to how much we can distinguish between, like if I want to distinguish between two quantum states by doing a measurement and you concentrate on one outcome, what is the difference in the probabilities between these two outcomes? Okay, what is the difference in the probabilities between these two events? And how do you get the outcome? By doing the most general thing, a most general quantum measurement. Even then, the distinguishability is upper bounded. So that's why this is probably the most important distance measure between two density matrices. Any questions about this? Okay, so let's move on. So let's start with on a new page. So we have seen measure of distinguishability within density matrices. Okay, we have like the right generalization of the one norm. Okay, now let us we're doing information theory, right? So first of all, we need measures of distinguishability. Okay, all these distances. Next, we need entropy quantities. So let's now define entropy quantities. Now, I want to define Shannon entropy of a quantum state. Okay, Shannon entropy of a quantum state. So remember my quantum state rho. So if I go to its eigenbasis, so I can write it as summation over I, lambda I, sum. This we saw already. Get Vi, bra Vi. So the Vi's are the orthogonal basis of eigenvectors, and lambda is the eigenvalues. And I know that the lambda is a positive and add up to identity. So the lambda is, I can treat it as a probability distribution. So I'm just reminding you, so I can think of a general quantum state to be a mixed state, to be a probabilistic mixture of pure states, ket Vi, okay, with probability lambda, right? So for probability distributions, I know how to define the Shannon entropy. So I just use the same thing, okay? So I define the Shannon entropy of rho to be the Shannon entropy of its probability vector of eigenvalues. Okay. So this is, if you recall, negative of summation I, lambda I, log lambda I. Okay. And there's a fancy notation, but it's useful to know. So this is, let's say, trace rho log rho. So I'm now using fancy matrix notation. So rho is a matrix, I know that. What is log of a matrix? So log of Hermitian matrices are now easy to define. Okay, or in general, I mean, if I have any function from R to R, okay, real numbers to real numbers, I can define f of rho, where rho is a Hermitian matrix in natural way. Just go to the eigenbasis of rho, okay, apply f to the eigenvalues, keep the eigenvectors the same. So f of rho is a new operator which is the same eigenvectors as rho, but the eigenvalues have changed from lambda to f of lambda. Okay. So here my function is the logarithm function, so I can define log rho, and you can see that this is independent of choice of the eigenbasis. Okay, so that is because you take any Hermitian matrix, so there might be degeneracy in the eigenvalue. So let us say lambda 1 is equal to lambda 2. But fine, look at the distinct eigenvalues and look at the eigenspaces for those eigenvalues. So the degree of freedom you have in the choice of the eigenbasis, that degree of freedom is only there for the repeated eigenvalue. So let us say lambda 1 is equal to lambda 2. That means the eigenspace for that eigenvalue is of dimension 2. Lambda 1 is equal to lambda 2, and then let us say lambda 3, lambda 4 are all different. So this particular eigenvalue, lambda 1, okay, has associated eigenspace of dimension 2. So the only degree of freedom is that you can choose any orthonormal basis for the two-dimensional space and call that V1 and V2. That's the only degree of freedom. But that's fine. Then if I have to define log of rho, I'll just take log lambda 1. Okay. Same thing is log lambda 2. And it does not matter what V1, V2 I use to span that two-dimensional space, the operator is the same. Basically, log lambda will look like log of rho will look like log of lambda 1 on that two-dimensional space. So similarly, let us say there is some other eigenvalue lambda 3, lambda 4, lambda 5, all three are the same. So it will look like log of lambda 3 in the next eigenspace. Okay. So
Um,
this choice of vectors will not matter within the eigenspace. Yeah.
Pranav, I've always had a question about this. So, yeah. So when Shannon came up with his definition, that was much later than this. Actually, this was earlier, right? As you, von
This was
Neumann or
slightly
something.
earlier. This was by von Neumann. Yeah.
So I mean, Shannon entropy makes sense if you like. There are treatments where you start from a bunch of axioms, and those axioms make sense for a
Yeah.
measure of information, and you get.
Yeah.
But this thing was even before all that, right? So I mean,
Yeah.
what are there any like physics or
Yeah.
any
Yeah.
axiomatic?
No, there are physics reasons. So this is
There are physics
basically,
reasons.
yeah, I mean, this comes from thermodynamics. So even before von Neumann did for quantum states, there was a notion of entropy for whatever gases, I mean, where
E-
molecules are treated classically.
Yeah, but they always assume that things are uniform and say entropy is log of the size of the space or
Correct,
something.
correct. But then if it is not uniform, I mean, it was sort of implicit that what do you have to do? You have to take the weighted linear combination.
I see.
Okay, so I
I
don't know
see.
if it was explicitly written somewhere in the literature, but I mean, it was implicitly understood by physicists of that time what you have to do.
Okay. Okay.
Okay, so when von Neumann was trying to define entropy, he was just thinking of thermodynamics. So he just defined it this way. He of course, I mean, knew physics also very well. Okay,
Mm-hmm.
so he defined it. So I don't know if it was von Neumann who first explicitly wrote this formula. Okay, but maybe he might have been. Okay, but he was definitely inspired by the folklore of classical thermodynamics.
Okay.
Okay, and Shannon was also inspired by the folklore of classical thermodynamics. Okay, when
Oh,
he came up with this formula, that's why he called it entropy. Okay, but I mean, but he realized that I mean this definition, and again, I don't know. As I said, maybe I mean this explicit formula was not very commonly written down in papers at that time. So, but Shannon wrote it down, and he realized that this will be a good notion of the amount of uncertainty. The axiomatic viewpoint is not by Shannon. That's by later people. I think Kinchain in the
oh,
Russian school.
oh,
So
that Kinchin inequality
Kinchin
wala
guy,
Kinchin.
he may have inequality, but yeah, I mean, he's a probability theorist. And
Mm-hmm.
after Shannon's work in 1948, then I mean, information theory wasn't taken seriously in the West for a long time. Okay,
Okay.
so maybe in the late 50s it started picking up. Okay, but from
Okay.
1948 to maybe 1958, for 10 years, it's the Soviet school. I mean, Soviet school was very strong in probability. The
Mm-hmm.
West at that time wasn't even doing much probability. Like Feller wrote his book in 1940, but he complains that other than him, nobody in the West is thinking of probability. Okay, so yeah, so basically there was a rich probability school in the Soviet Union and in the Eastern Bloc.
Mm-hmm.
So they really took it up, and it's Quintin and then Reni, okay, Hungarian. Okay, so in the
Right.
mid 50s, they really, I mean, saw the beauty of what Shannon had done and took it up seriously, and they came up with axiomatizations. And so I think Kinchin might be the first one to show that Shannon entropy is the unique one satisfying the axioms. And then Rennie took it one step, said, suppose I drop some axioms, what are the new kinds of
Functions
entropies
that
I
I can.
come? Yeah,
Right.
he came up with his family and all. So it all came from those axiomatic mathematical viewpoints. Then even the rigorous proofs of noiseless source coding and noisy channel coding are by the Soviet school.
Oh, rigorous as in
Shannon's proofs
Shannon's
are not
paper.
rigorous. Yeah. So
What?
I think it's probably by Kinchain himself.
Oh, okay. So all
Okay.
the arguments that we learned, it's more
Yeah,
Kinchin.
yeah,
It's
yeah, yeah.
not.
It's Kinchin, and then other Hungarians come Scissor and Corner, but that's in the mid 60s. Okay,
Mm-hmm.
they are the people who really made it rigorous.
Okay.
Okay, so and I mean you can see like Kinchin makes it rigorous and says, oh, by the way, I don't need IID sources. This will work for memoryless Markovian sources and all that. All those things. I mean, they were experts. They did that.
Okay.
Yeah. So the treatment that we learned today is actually we owe a big debt to the Eastern Bloc.
Okay.
And then in the mid 60s, I mean, information has started picking up, and some of those papers got translated into English, and then uh, these other guys, Cover and company, started reading them.
Gallagher. Cover.
Gallagher, yeah.
Hmm.
Okay.
Okay.
So yeah, I mean, von Neumann also is Hungarian. I don't know. I think when he did it, he was probably whatever in Hungary, but this will be like 1930s,
Mhm.
either in Hungary or in Germany. One of the two places. Or in Austria, not in Germany. Anyway, yeah. So this is the definition of the Shannon entropy of a quantum state. Exactly analogous to this. So then you may remember that, let us say I have a probability distribution on the sample space AB, and if it happens to be a product distribution, okay, then I know that H of AB under the distribution P is equal to H of A under P plus H of B under P. Okay, so I know this. So you can expect the similar thing will hold. I have a density matrix on AB, but it's a tensor product density matrix. Okay. So now if you take tensor of two matrices, okay, and let's say tensor of two Hermitian matrices, express the first Hermitian matrix in its eigenbasis, express the second Hermitian matrix in its eigenbasis. So when I take tensor product, let's say I take tensor product with respect to eigenbasis. So you can see what this looks like. So this will also be a diagonal matrix, the tensor product, and you'll see the eigenvalues that are formed by taking pairwise products, okay, of lambda I from the first guy times mu j from the second guy. So as you can expect, the same thing will hold here also. Okay. So really the probability vector of eigenvalues becomes the Cartesian product of the two probability vectors. Right? So is it clear, Hari?
Yeah.
Yeah. Okay. So far, so good. Things are analogy. Now, let me come up with a shocker. Okay. So far, like, I mean, everything went analogous to the classical theory. So, okay. So, let me write. So here is a big point of difference between classical entropy and quantum entropy. Classical fact. Okay. So take a distribution PAB. Okay, P on the sample space AB. Now, it's a general joint distribution. I know whatever joint distribution it may be, I know that the entropy of the joint system under P is definitely greater than the entropy of its constituent. Right? Hari, you have seen this, right?
Yeah.
Yeah. So one may believe that this is true quantumly. Okay. So same setting, rho AB, it's a general density matrix, maybe entangled quantum state. Okay. So H AB rho. So the previous question, I put a question mark. H A rho. Okay. So actually this is wrong. Okay. So this is wrong. This does not happen in general. It may happen, it may not happen. Okay. Oh, yeah, before we go ahead. So the entropy is always non-negative, right? So that you can easily check, easily see from this definition, of course. Entropy is non-negative, and same thing. Entropy is zero for pure states only. So when I have a pure state, that means lambda 1 is 1 and the other lambdas are all 0. Okay. So only for pure states, the entropy is 0. So pure states are the analog of the delta probability distribution, the probability distribution that are concentrated at one point. Okay. So entropy of pure states is 0, entropy of mixed states, okay, in general is greater than 0. And the maximum entropy is a log of the dimension of the space. So all these things easily follow. Okay. So no surprises there, but here is the surprise. So let us see. So can you come up with an example where this goes for a toss?
Yes.
I mean, yeah, I know you can. I'm waiting for it. So I know it's hard, but I've actually like whatever I've taught you so far, you already know the example.
Yes.
So I'll give you the time. Yeah. So we have about half an hour. So I'll give you 5 minutes, Harif. So think about it. Okay. So look at the kinds of states that we have studied, okay, and see if some famous state violates. So I'll just pause the recording. Resume recording. Yeah. Yeah. So any luck, Harif?
Yeah, so maybe like if this is like entangled thing
Yeah.
going on. If
Yeah, it's that tangle thing going on. And in fact, as you can see, like, I mean, if you just use systems AB, like, as you'll realize very soon, it's in fact a signature of entanglement in a sense that if you have an entangled pure state, this inequality will be violated. Okay. So let's first see the example. So in fact, I'm telling you that here is a pure state. So it's our famous EPR state. So it's a pure state. So of course, I mean, if you're thinking of the density matrix, you take the bra of it also, get bra. Okay. Now, because this is the pure state, okay, we know that the entropy so because this is a pure state, the entropy of AB under rho will be 0. Okay. But let us look at the entropy of A under rho. So rho A, remember we had done this calculation. So rho A is the marginal state obtained by tracing out B. So this turns out to be probability distribution. So it is a probability distribution which is half probability on CAD0, okay, on the pure state CAD0. So half probability on CAD0, half probability on CAD1. So in other words, this was like identity on A divided by 2, which is so. Okay. So the numerator, of course, is identity, and it's divided by 2. So now, so again, you know what is the entropy of this? This is in fact the maximum entropy that a two-dimensional system can have. This one. So an amazing thing happened that h of AB is 0, but h of A, okay, is much bigger. It jumps from 0 to 1. So in fact, I mean, A here was like 1 qubit, but I can take n qubits for A plus n qubits for B. Then I can come up with an analogous entangled EPR state, okay, for AB. And because it's a pure state, entropy of AB will be 0, but entropy of A will be log n. So this jump can indeed be stupendous. So example is clear?
So I just have a comment. I mean, maybe this is a very obvious comment, but the thing is, this only happens because the definition of entropy sort of ignores the geometry. It doesn't depend on which basis or how things are defined. That's why when you go up to a purification, you essentially have a new matrix, which is a rank 1 matrix. But entropy doesn't care about that. Entropy just says, I'm only going to look at the eigenvalues. I don't care what is underlying. But the moment you come down, you have a matrix of larger rank because of the specific geometry of this kind of thing. But then your entropy can blow up. So this happens because the definition of entropy is ignoring geometry pe kya ho raha hai. It's more like it's only bothered with eigenvalues or something. That's
yes. But I mean, that is what entropy is meant to be. Entropy is meant to, even in classical probability, I mean, you take a probability distribution, if you commute it, you don't change the entropy. Okay. So entropy is really concerned with the distribution of probabilities.
But this is more than permutation, right? Permutation, if you permute it, okay, I can understand, fine. But this is much more than permutation. This is bending. I mean, you might be rotating the space or bending the space in a higher dimension. Entropy doesn't care.
Yeah, well, I mean, more to the point would be that, I mean, this is where the quantum behaves very differently. Look at it the other way. Like you go from system A to B. So classically, it can never happen that classically, it can never happen that the support of the probability distribution on AB is smaller
than the support of
the support of. Okay,
right.
But quantumly, that can happen. Okay, so that is to do with this weird property of the partial trace, or if you're saying reverse. So here, like support of rho A is a space of dimension 2, but support of rho AB is a space of dimension 1. So it's more related to that. Yes. So this is the difference. I mean, fundamental difference between classical probability and quantum. In quantum, really, the Hilbert space geometry, geometry of vectors starts kicking in. Okay, and it can do very non-intuitive things at certain places. Yeah, so this is a big point of difference. Okay, so the question is, I mean, is all hope lost? I mean, I just told you like entropy of AB can be 0, entropy of A can be log n. Okay, if I'm doing the same example on n plus n qubits, so I mean, this looks really bad. So do we have some handle on how bad this jump can be? The answer is yes. So this is called the triangle inequality or entropy. It is also known as, after the mathematicians who proved it, Archimedes. So if this says the following, that entropy of AB under rho is greater than, so I cannot write entropy of A out here, but I can write entropy of A minus entropy of B. And you can put an absolute. So basically, all I'm saying is that it is greater than entropy of A minus entropy of B, or if this is negative, I'll take the other one, entropy of B minus entropy. Okay. And you can see that this inequality can be saturated. So again, the EPR state. So here, entropy of A is 1, entropy of B is also 1. The difference is 0, and that's exactly what you get. Okay. So, in fact, you take any pure state on the system AB. Okay, entropy of AB will be 0 because rho is pure on AB. Okay. So that means that H of A should be equal to H of B. just abstract. Is this clear? So for any pure state, of course, entropy of AB will be 0. And then I also know that if I look at its subsystems, the two subsystems, they should have equal entropies. So let us see this picture in little more detail for pure state. So let us say I have a pure state rho on AB. Okay, because in general, entangled pure state. So I know just by this hammer of Arakiliev that entropy of A is equal to entropy of B. But let us see if I can prove at least this fact in a more elementary fashion. And here is how I'm going to do it. So this is a vector, so I can write it. So fix some computational basis for A, computational basis for B. So I can write it as sum over AB. So let us say rho AB like this. And so this is a complex number, of course. This is some complex coefficient. And cat A, cat B. So this is the vector in the Hilbert space A. This is vector in the Hilbert space B. There is, of course, this tensor product here. So I mean, often I load it to save notation, but right. So I'm just writing down a general vector in the tensor product space. So now what I'll do is that, remember AB was computational basis vector, so it's an orthonormal computational basis.
Sorry,
So
I'm not just one thing. So are we proving Arakiliev?
No, we are not proving Arakiliev. We are proving a consequence of Arakiliev that if
For a
rho
pure
AB is
state,
a
HA
pure
equal to
state,
HB. Okay, got
yeah,
it. Got
HA is equal to H.
So I mean, just to say, without going the more elementary, which using Arakiliev, it's just this, right? That mod of HA minus HB is 0, so
Yeah,
they
yeah.
must be equal. Just
Yeah,
that,
yeah.
right?
It's just that, yeah. But I mean that we are assuming a non-trivial theorem like Arakiliev. So I'm just going to prove the same thing by elementary. But on the way, we'll learn something beautiful about geometry of entangled states. Okay. So yeah, so I took a general state, in general entangled, write it in the computational basis. So I'm just collecting terms like this. Now, so of course, I mean, I said computational basis. That means, what does it mean? Like fix an orthonormal basis for A, fix an orthonormal basis for B once and for all, and then I can write this. Now, suppose what happens if the computational basis for the system A that I fixed happens to be the eigenbasis of rho? No. So let me ask this: what happens? If this set of vectors is the basis. Okay. So let's note what I mean by this. Note that I'm not claiming that this A tensor B is some eigenbasis for rho AB. In fact, that's not even true, because this is a vector rho AB. So if I treat it as a density matrix, okay, it's a rank 1 density matrix. So it has only one eigenvector with eigenvalue 1. The other eigenvectors have eigenvalue 0. And the eigenvector with eigenvalue 1 is this full expression, this full summation. Okay. So in fact, this ket A tensor ket B cannot be an eigenvector in general of the density matrix rho A. So that's not what I'm doing. So this is just an expression of the vector ket rho AB in terms of some orthonormal basis of A that I fixed once and for all, and some orthonormal basis for B that I fixed once and for all. So after I fix it, I can write it this. Now my question is, what happens if this choice of orthonormal basis that I've done for A happens to be the eigenbasis of rho? So here is where something beautiful happens. Let's see. Okay. So fine. Let us write down what the reduced state rho A looks like. So rho A.
Can I
Remember what?
hazard a, can I take a guess or something? Then
Guess for what?
yeah, so these vectors, the ones in the brackets, they would be orthonormal if corresponding to like A and A prime, they would be orthonormal.
They'll be orthogonal.
Orthogonal.
They'll be orthogonal, and then I mean I'll remove some scale factor
Yeah.
and make it orthonormal, and I'll interpret what that scale is also.
Right. Okay.
So let's give a name for this. Since I said this quantity in brackets, so let's call it V sub A. Okay, this is just a shorthand for this. So V sub A is a vector in B, and it is in general not even unit vector. Okay? So not unit length vector. You can easily see because I mean I take this vector VA is the sum of the length squares will add up to 1. I mean this overall thing is a unit length vector, right? So what I'm saying is that in fact I can even say more. VA 2 norm square. Okay, if I add up, gives me 1. Is this clear? Summation over A VA 2 norm square is 1. That is just because. Okay. I mean there is this orthonormal ket A sticking out here. So this is basically looking like ket A on the system A, and this is ket BA on the system B. And now if I look at the L2 length of this vector, so I mean length square, it will just turn out to be this. Okay. So far so good. So let's do this calculation. So, okay, so this one was ket rho. Yeah. So rho A trace out of this. So let's write down. So what is this? This is trace out of B, and this is ket rho AB. This is ket rho AB, pure state, right? So rank 1 density matrix, and bra rho AB. So this is some compact notation I have for that. So I can now write summation. I'm explaining A prime. So ket A BA. So A B, and now bra A prime. This is A. This is B. Right? Just I'm taking ket bra. And this is further equal to. So I know we've seen this property of tensor products. So we can rearrange things. Summation A prime. On A. And this is tensor product. V A B A prime. Right? So let's okay. Now so far so good. Now I know that this has to be rho A. So if I trace out B, this thing should be equal to sum over A, some let us say lambda A, which is the eigenvalue corresponding to eigenvector. Remember, A was the eigenbasis for rho A. So this should look like this. Now, this expression should equal this expression. And remember, like A is an orthogonal basis. So the only way this expression can equal this expression is if it is equal term by term. So what this implies is that trace of so when I do the maybe I can put in one more step out here. If I was Arun, I would have just moved it down, but let me write it here. So this is summation A prime. And I have this partial trace over D, right? So that just goes here, and I have the trace of this operator. Right. This is so what I have trace of VA prime. Okay. So this is equal to lambda A, then the Kronecker delta symbol on A prime. Kronecker delta just means that if A is not equal to A prime, it is 0. So all I'm saying is that if A is not equal to A prime, this trace is 0. If A is equal to A prime, this trace is lambda A. Okay. But I know what is this trace. It's a trace of ket bra we already saw previous lecture. What is it? It is just this. Bra VA on the left and ket bra VA prime on the left, and ket VA on the left. Okay. So this is what I've proved. So again, to refresh your memory, so one quick way to see this equality is like, remember this ket is an operator from I mean, it's a linear operator from a one-dimensional vector space to a n-dimensional vector space, in this case, b-dimensional vector space. And the bra is also a linear operator from a b-dimensional vector space to a one-dimensional vector space. So this expression is just the product of two linear operators, product of two matrices. So product of n by 1 matrix times 1 by n matrix. Now by cyclic property of trace, I can move this to the left. Okay. So now this is a n by 1 matrix, a 1 by n matrix. The product is a 1 by 1 matrix. Okay. And we know that we can interpret this as the inner product between the vectors. Okay. Yeah. So just reminding you of this manipulation. So this is what I'm doing. So as Shanton says, if A is not equal to A prime, these vectors become orthogonal. If A is equal to A prime, then this is just the length square of the vector. So what do I have? Like, so V A prime, VA equal to 0 if A is not equal to A prime. And if it is A is equal to A prime, this is the L2 norm square, which is lambda A. Okay. So what have I concluded about this vector? It is VA. So the VAs are orthogonal for different A's, and the length of VA is square root lambda. So let us use that fact. So what have I concluded? I've concluded that rho A B can be written in this special form sum over A square root lambda A, and let us call it WA after orthonormalization.
Can I not always
So
map?
this is eigen basis, eigen basis of rho A. And now you can check. I mean, so now W are an orthonormal family. You can check that this is the eigenbasis of rho automatically. That's the same reason. So eigenbasis. Okay, so this is a very beautiful thing. This says that you take any any vector, okay, in the tensor product space. There's a special way of writing it. Okay, how? So take this vector, treat it as a density matrix by doing ket-bra. So I get rho AB, it's a rank one density matrix, no problem. Look at its reduced states, rho A and rho B, find their eigenbases. So call call those eigenvalues. Let's say the first one I call A, and then there is a pairing. Okay, there is a bijection between the eigenbases, eigenvectors of A and the eigenvectors of B. So that is the map A to WA. So there is a pairing, and then with respect to this pairing, there is this decomposition, and the corresponding eigenvalue comes out. So this is a very important algebraic and geometric property of a general state in a tensor product space. Okay, and it goes by the name of the Schmidt decomposition.
So just to be slightly clear, so the point is that when you fixed the basis on A, you essentially fixed it to be that basis which is the eigenbasis for rho A.
Correct.
We started off with that, and then you said,
Yeah.
okay, fix any other basis on B, write it in like a usual some sort of decomposition with respect to that basis, and we can then conclude this.
Yeah.
Okay.
Okay. So now what is this telling us?
But
So once
I'll just interrupt you for just once. So isn't this the following an easier proof? So you take rho A, and maybe it's even the same proof, but I just want to say it. So you take rho A, ket bra A, okay? Then you say that I'll give you a mapping, and that mapping will do the following. It will map ket bra A to ket A, but the second ket A will be on the B system, okay? So this will be some purification of rho. Let us call it rho A B prime, okay, or rho prime A B, whatever, rho prime A B, okay. Then what am I going to do? I'm going to come up with a unitary which maps A to any other basis of my choice, say WA. So A to WA. So and that unitary exists, that I know. So once I apply that unitary, I recover this exact state that you have written here. So
well,
that
the
is
existence of that unitary follows from the Schmidt decomposition, the other way around. So the existence of the unitary that you're talking of, okay. So you're basically saying that any two purifications are equivalent by a unitary in the other system.
yes.
That actually comes from the Schmidt decomposition.
Oh, okay. Okay.
So this is what you have to prove.
Okay.
So
okay.
there is an alternate way of proving it but it's kind of messy and basis dependent. So yeah, so this is basically for the expert Shanton. So you take this vector and convert it to an operator by the op technique. So now the vector rho AB, I'm now thinking of as a linear operator from B to A. And you look at its singular value decomposition. Okay. So you get left singular vectors on the system A and right singular vectors on the system B, and they will be these guys.
Okay, got it. Yeah.
Okay. And the singular values will be the square root lambda.
Okay. So you go from the SVD, you essentially start with the SVD, you go from SVD, you apply the op and you get the purification. Or is like
no, the other way. I mean, I start off with the
other way. You start off with the
purification.
purification.
Yeah.
Yeah. You start off with the purified vector, write it in this thing. So this is given to you. Then you op, map it to the map it to the operator. Then you say that okay, this operator has an SVD, and that's it. That's lambda.
One way of doing it, but I mean,
yeah.
But
Yeah,
again, I mean, that's not a very transparent. This is very nice.
Yeah, this is
this
very
exactly tells you like, okay, so it tells you nicely. Okay, so Shantan is repeatedly using the word purification. So what does he mean by that? So it's just this, that I have a state, I have the reduced state rho A, and I have a state rho AB with the property that it's a pure state. So that's why it's ket rho written out here. It's a rank one density matrix. And if I start off with the pure state rho AB and then trace out B, I get back rho A. So this process is called a purification. So you have a general quantum state on rho A. I have extended to a quantum state on rho AB, which is pure.
So in fact, this proof has a very nice thing, which maybe like it's obvious to you, I don't think, but basically those rho AB coefficients that are there, those form the entries of a unitary. That is clear from this VA prime VA orthogonality property. So that is very pretty. That I noticed. It's a very pretty thing.
Yeah. Anyway, so
Yeah.
so whatever, like
Yeah.
so what have we? I mean, what is the take home thing? You take a general entangled state, okay, a general state in the tensor product space. Okay, I can write it in a special decomposition. Okay, so the special decomposition tells us something. So the orthonormal basis of A that I take is the eigenbasis of rho A. The orthonormal basis I take for B is the eigenbasis of rho B. There is a bijection between the eigenbasis of rho A and the eigenbasis of rho B. Okay, and after I get the bijection, I can write it like this, and the eigenvalues of rho A, which also happen to be the eigenvalues of rho B, okay, appear out here with square. So this, I mean, full thing is called the Schmidt decomposition. So this automatically tells you that like rho A and rho B, they of course have different eigenvectors. I mean, one is A and the other is WA, but they have the same eigenvalues. So their entropies are the same. So here is one way, but yeah, but the Schmidt decomposition is beautiful. It tells you a lot of other things. Really, it's my pen. So I can't find my pen. Anyway, I think I'm done. Okay, so any questions? Okay. So if not, we'll stop, and yeah, we will get deeper into the study of entropy quantities in the next lecture.
Okay. Okay.